Good afternoon and welcome back. Sorry for the technical difficulty there, but we're glad you've rejoined us and we're ready to get started. We wanted to do just a brief review of what we did last week, just to kind of refresh, and then we're going to take you through the rest of the units in the UJEEP STEM workshop. Just keep in mind that this is part of the OSLN Design Challenge preparation, so keep thinking about what might be a hook for your students and what ways might you be able to engage them using these activities to get them started thinking about that challenge. And again, we want to thank the sponsors, UJEEP, Battelle, OSLN, Battelle OSLN is together, I guess, and then OEP, which will be the session next week. So last week, we talked about formation, and one of the key words we talked about was biogenesis, and that capability of all of those microbes in the ocean marine environment to actually break down some of those living things and turn them into hydrocarbons. The next unit was the migration and trapping unit, and really the key words in that one were porosity and permeability, and we used the baking rocks activity. Exploration was our third topic, and we used that topography, coming up with a contour map, and also a topography exercise, so students understand landforms on the surface as well as landforms under the ground, and that's how we look for oil and gas. And then the fourth unit was the drilling and well stimulation, and we finished with the Twinkie activity. Hopefully you enjoyed eating that after the fact. Or not, but then we talked about drilling, so directional versus horizontal versus vertical. So just kind of reminding you of those things will get us started here, and I'm going to turn it over to Heather so she can talk a little bit more about what we're going to do tonight.
Sure. So today we're going to go ahead and work through the remaining 3 units. Can you put the slide up that has those units just to refresh the teachers with that? So what you'll see here is as we're working through this UJEEP curriculum, we want to be hopeful that you will continue to add to the chat some of your comments about the lessons as we move through them. So if you have some suggestions, things that you like, we'd love to hear your reactions. It really helps us as we're moving through. So please keep your cameras on tonight so that we can see your faces. We can see if we need to take more time for an activity or not, based upon the reactions that we're seeing, as you know. So the majority of lessons after this first one, pipeline pigging, they're all brand new lessons, and we would really appreciate any feedback that you have as we're moving through those.
For sure. All right, so let's start with Unit 5. And Unit 5 is producing and transporting, and we should have a slide that talks a little bit about, okay, so there's all the 7 stations. There we go, one more. So you can kind of see through this graphic that there's a lot that happens after the oil and gas come out of the ground. So we're really looking at how do we get it from point A to point B. So if we can go to the next slide, there's a few things here. We talk a little bit, background here would be like a wellhead. So we've had the drilling rig on the site, that was last unit, and now it's moved off. Now there's a wellhead that's actually going to contain the pressure and monitor and be able to hold that well, so that when we want to produce from that well, that there's a way to do that. The crude oil, the natural gas, the brine water all come to the surface. And then when they come to the surface, they need to be separated. So this is a great opportunity to talk to your students about those properties of density. So obviously your natural gas is going to be at the very top and it's going to be captured. Then your water layer is going to be at the bottom and your oil layer is going to be in the middle. And so all of those things need to be separated, and there's usually a separator on site. Natural gas might initially enter a pipeline right from the wellhead. We have a lot of pipelines that are doing that and taking it directly to compressor stations so it can be transported. And the thing that we're going to spend our time on this afternoon is do something called pigging. And it's an interesting reason why it's called pigging, but we'll kind of ask in the chat and for you to suggest reasons why we might call this pigging. But the oil and gas that comes out of the ground and goes through these pipelines is sometimes has some debris. So it's not necessarily dirt or things like that, but the crude oil that's coming out of the ground, it changes in, it has a lot of variation to it. So the oil and gas that we produce, or the natural, let me slow down. The crude oil that we produce has a lot of wax to it. So if you have M&Ms and you've had M&Ms before, they don't melt in your hand, right? Well, that's because they have a waxy layer on them that actually comes from crude oil that's produced, or like the crude oil that's produced in Ohio. So that waxy buildup obviously is in those pipes. And if we're putting oil through a pipeline, we're trying to get that oil from place to place most efficiently, and we want to make sure that that waxy buildup doesn't start to impede the progress of that oil. So we're going to do an activity called pipeline pigging, and it's on the page after the 5, producing and transporting background. And you're going to need the package in your kit that contains the pipeline pigging materials. Probably rollers,
Mhm.
should be some string,
Yep, she's got it. I see Sarah's
cotton
got it right
balls,
there.
yeah,
Yeah, so
and a PVC pipe.
yeah. Okay, great. So once everybody has those materials ready, go ahead and pull them out and place them on your table in front of you. This is a great engineering activity that we do to help students problem solve some ways that will help us as we are producing crude oil and bringing it up to the surface. So as Jane mentioned, in many areas of our state as well as across our country, we have a lot of we have a lot. I'm so sorry. Stop giggling.
Sorry, I couldn't help it.
We have a lot
someone
of,
rolling his hair.
yeah, we have a lot of
Could avoid it.
difference. We have a lot of differences in the integrity of that oil. And so, the different densities, different makeups. And so, like she mentioned, here in Ohio specifically, there's a lot of wax. And so, just take a minute and pull up this PVC pipe and just, think about if we had a very waxy crude oil substance moving through this particular pipe, what could happen to the pipe? So I like to start this lesson asking students that question. Here is a means of transport to bring the product from thousands of feet below the ground up to the surface. And so as that product is moving through this pipe, what could happen to the pipe? Or what are some ways that it could impede, as Jane mentioned, the efficiency of removing that product, et cetera? You could even model it off of maybe some heart disease. Students might be familiar with cholesterol and clogging of arteries. It's kind of a similar concept in some degrees when you're talking about the wax. And so obviously the industry has faced this problem, and they produce some machines. They're now usually powered, or they're magnetically pulled through the different pipes that help them to keep them clean on the inside, so that the product that's coming behind it can move as efficiently as possible to the surface. So we're going to challenge you today to create a pig, is what they're called, that will move through your 2-inch PVC pipe and actually clean it. But there's a few things you need to consider. You've been given several materials. As you can see here, Florian's gone ahead and show you this picture of our materials that we have here today. You can use anything in your classroom. These are just some suggestions, some things that we usually send out to teachers so that the teachers know that, it's just a good skeleton to begin with. But you don't have to use these materials. These materials can be really anything. You could use things like toilet paper holders, for example, obviously tape, paper towel holders, anything like that, to give the students a skeleton to build upon, okay? So as you look at these materials, I want you to think about the properties of these materials and how you can best use those materials to clean out the inside of your pipe. Okay? Now let's review some of the materials that you have here in front of you. You definitely have a string, and yes, I'm going to ask all of you to attach this to your pig once it's created and to pull it through your pipeline to make sure that it's effective. Okay, so that'll be our test. And if it pops right out, is probably not super effective, and you might need to redesign a little bit. So we're going to use that engineering design practice to improve upon our previous work so that we're both moving through the pipe at a good pace, but also effectively cleaning that pipe as well as we're moving along. We don't want it to come out, really hard, or that's not going to be efficient either, because you're going to be backing up a product behind it, right? So let's all take a few minutes. You can use any of these things here in front of you. There's various hair rollers that you've been given. Sometimes you get hair rollers like this one that kind of have a clip on. I think I saw Andrew putting that up in his hair earlier, which is a good idea. Sometimes you have these Velcro rollers, which help students sometimes because they do have a bit of a friction on them, so you can see how those might clean out that pipe. Okay, and then you have some other things that can help you increase your surface area. So you have cotton balls, you have pipe cleaners, some Q-tips, even some bobby pins, I believe, that will help you to attach things to your hair rollers or increase your surface area so that you can utilize that and move through the pipe. So remember, the force today that you will use to pull your pig out of your pipe is your string. So please make sure your string is firmly attached so that you can pull it through your pipe. And you want your pig to come in contact with all of the inside of that pipe, so that whole surface as it's pulling through. Okay, so we're going to give you about 5 minutes maybe, or a little less?
Yeah, 3 to 5.
3 to 5 minutes to begin to create. And don't overthink it, because remember, as engineers are creating, they have first an idea, and then they try the idea, and then they go back and improve upon their idea. It doesn't have to be perfect at first. Okay, so Jane and I are going to make one too. Sound good? You can choose whatever you want. What are you working on, this one?
Yeah.
Okay, I'm going to use this one then. You can have this bigger string.
I feel like we should be playing the Jeopardy song.
I feel like we should
just
be
in memoriam.
Mm-hmm.
It was a sad loss to game shows.
Yes, it was. I suppose we could have some music play if they want to send that along. Okay.
Sure.
Yes. So we had a great question. Can we modify anything that I sent to you? Absolutely. The only thing you cannot modify is the PVC pipe. Okay. You are the creative engineer, and you're allowed to utilize the materials that are given to you to the best of your ability. I'm even using a pencil and, to try to skewer this thing.
And that is, one of the keys here is you can be as creative as you want in terms of providing materials to your students to use. And at our in-person workshops, we typically have a little contest and people vote for the best pig.
Absolutely. And while you're making this, please, think about, why do we call them pigs? I'm struggling today. Usually I can make one pretty quickly.
I'm having a lot of trouble with holding my things in place.
Mm-hmm.
This reminds me of...
I think it's really interesting, because as you're making these with your students, you should have your students explain why they're using the materials that they're using. So Jane and I are both trying to be kind to each other and not steal the other materials, but it's going to become a challenge here pretty soon, I have a feeling.
Let's try and make it so it does what it's supposed to do.
Mm-hmm.
Uh-oh.
So another question that we had is, does the size of the hair roller matter? We don't think so. Again, you can use toilet paper rolls. You could use just crumbled up paper. Whatever you have available, or a student in this current time has available at home. I would encourage your students to be creative. Really, you just have to be able to move along the inside of the PVC pipe and effectively come in contact with it in a way that it still will move and not hold you up. So I would say no, because you can always build upon something unless, of course, it is too big to fit inside of your pipe. And you could also challenge students to use the least amount of materials, because remember, it is a business and industry will make sure or need to be able to afford these things that are moving through their pipelines to keep them moving as efficiently as possible too. So you could give them a budget. There's lots of things that you can do. Okay. Are you ready?
I'm ready.
All right. Let's see how people are doing. Give us a thumbs up if you're feeling ready. Oh, okay. We got a couple people. Good.
We'll give you another minute or so just to finish up if you have some final design
Challenges
pieces you want to add.
I do feel like we should have typed in some music.
Well, something to think about while your kids are operating in this. If you're in a virtual space, that might be something that you could find some timed music online, and then when the music stops, they need to be finished.
Yeah.
That's one opportunity for you. Or you could have it just a timer, so everybody has the same amount of time. Or if you have access to music files. So not sure if everybody wants to play their playlist in front of their students, but some might.
Oh, kids will listen to anything, I think, as long as it's appropriate. They'll be grooving. I think I'm just leaving it as it is. I feel like I should continue to build onto it.
I don't think there's anything necessary.
Do you need any tape? Are you good?
I don't know. I suppose I could tape it, but then it seems like it would
be less
change
effective.
Change the integrity a little bit.
All right, you guys, let's see what you have. I'm going to explain my design and show you how possibly it can move through. I see some creative examples there. Okay. Ooh, she used hers 4 times, or Andrew did. Forgive me. I see that he's got 4 rollers inside of something in his pipe.
Took them apart.
Yeah, good idea.
The clip part.
Okay. So I don't know what you have on the outside of your rollers, but perhaps Andrew, as it's moving around in there. Okay, and that's the other thing. How do these move through the pipes? Remember, they have to continue to move along for thousands and thousands of feet at a time. So in my design, I'm actually going to put it in here and just pull it out. I took a very simple route, and I just used a Velcro roller and broke apart my cotton ball on the outside, and luckily it sticks to that Velcro roller. I have a bobby pin that went through to hold on to my string so that I could pull it from the middle and get the best movement there. And then to help keep everything straight, I put a smaller Velcro roller with a little holder for my string up here so I wouldn't lose it in the process. So maybe it's just best to do it this way. So another thing about a smaller front is that it will help to kind of allow this to move through a little bit better by being a little more aerodynamic. So on my screen, you can see that as I pull it through, it just goes right through. Leaves a little bit of fuzz behind though. How does yours work, Jane?
So you might need to
deal
with that.
I mean, I can't leave debris behind.
No.
So that is a problem, and that's something I have to fix as an engineer.
So mine's not quite as attractive as Heather's, but I wanted to make sure that I have these little cosmetic sponge type things on here. They're just little pads.
I think they're flat cotton things.
Yeah, flat cotton. So I'm going to try to, I have a lot of string.
Mm-hmm.
So I'm going to put the string through first. So mine could go very far, many miles. And then hopefully you get it lined up. I put this tape on so it wouldn't fall off. And then,
ta-da! Woo! Woo!
So it's going to clear out a lot of debris, but it may not last very long. It's not very sturdy.
Well
So
put together. So there's challenges that your students might have to face. I mean, you might even line the inside of your PVC pipe with a few elements in there, maybe some just vegetable oil or Vaseline or something to see how they could mimic it a little bit more realistically, what's done in the industry or process. You might even challenge your students to be able to create some form of movement. So Jane and I were simple and we just pulled ours through, but you might ask them to have it move in a rotational manner to make sure that it's effectively cleaning and not leaving streaks as it moves up and down the pipeline. I think it's interesting that students will come up with lots of different ideas.
yeah, can you show us yours?
Yeah, we'd
Everybody
like to, if
hold up your
everybody can
camera.
hold them. Ooh, look, hold them up. You can hold them up in the tube if you want. Okay, you can hold them up individually. I see one that's even pink like a pig. Nice, very nice.
Yeah.
Great. I don't know if we can get a picture of that, Shelly, or not, but if everybody could hold them up together, that would be awesome. We'll get a photo. Yeah, even with the smile on your face. One kind of looks like cotton candy. I like it.
Uh-huh.
Yeah.
Yeah.
All right, on the count of 3, guys. All right, 1, 2, 3. Well done. Thank you. I like all of your digital backgrounds too, by the way. They're coming in nice and clear.
There are a few things about the real pigs that they use,
Mhm.
and some of them are called smart pigs. So they actually will be kind of collecting data as they move along the pipeline. And these might be used like in Alaska or in some of the above ground pipelines. There's going to be a spot where the pig goes in, and it's either pressurized and moved or motorized and moves through the pipe. And then there's a point where the pig will be retrieved. So there's a team that goes and retrieves the pigs. I'm not sure I'd want to be on that end of the job. But so there's lots of different pigs out there. And so if you Google pipeline pigs, you can see different examples of those. And your students might really get a kick out of seeing the differences after they've had a chance to build their own.
Yeah, and I believe in the digital resources that are on this particular lesson on Ujip, you will see some samples of some videos there that you can reference for your classroom too. So we did ask you a challenging question. Why are they called pigs? I don't know, Shelly, if there were any answers in the chat.
Any guesses?
No guesses in the chat. Oh, man. No winner, no chicken dinner. Any questions? We're going to, oh, I see something. Oh, okay, I guess not. Well, there you go.
They do. They do squeal as they go through. I like that answer too. They like the mess. Yeah.
So,
it's good. Yeah, they apparently, as they run by a spot, you can hear them inside the pipeline, and they do make a squealing noise. So that's one of the reasons why they're called pigs.
Yeah, so I'm curious if they make a squealing noise because of the motor that's moving through or the friction as they move through.
Could be a little bit of both.
Yeah, for sure. Okay, guys. All right, so we're going to go ahead and change our table out. We're going to ask you guys to clean up and just put that aside in your bag that you had. The next lesson that we're going to do is called ink chromatography after we take this poll break. Okay, so if you could take a moment and answer the poll questions, we'll see you back in just about 2 minutes.
All right, welcome back. Hopefully you were able to set that aside. We probably should have told you to get your other materials. We're going to do ink chromatography and
Then we'll do classroom cracking
classroom cracking.
and build a hydrocarbon.
So we got 3 different activities we're going to do in this section. So if you don't have those materials nearby, make sure you can grab those here in a minute.
So
Can you
just,
take the poll down?
yeah.
I don't know if it's still showing, but we still see the poll. Thanks.
Okay.
So if we can have we're going to do just a little background here. This is Unit 6, so it's all about refining and processing. And that is where the money is. I just have to say it because we're taking this crude product, crude oil, and also natural gas, and we're creating many, many hundreds of different types of materials out of it. So, we oftentimes kind of think about crude oil as only being that goes to the refinery and we get gasoline, but we get way more things than that. So this unit really is talking about how do we get those things and how do we, what's the chemistry behind some of that. So if you can put up the slide, there should be a couple slides here.
There you
yeah.
go.
So basically, these are very long hydrocarbons. All right. So these are carbon chains that might be hundreds of carbons long, and obviously that creates a little bit of a problem if we want to actually get something out of it besides just the crude oil itself. So we figured out a way to separate all of those products or separate those hydrocarbons into smaller bits. And so that's what we're going to try and illustrate for you today. The different hydrocarbons then, they can be separated by boiling points, but they also can be separated by a process called cracking, which also uses heat and energy to actually pull those hydrocarbons apart. Different fractions then can be cooled and made into various different kinds of products. So we have lots of downstream industries, is that right? Downstream, where we're actually taking some of those products that come out of the refinery and further processing them into things like different types of plastics. Think packaging. Like how many different packages do you open each day and how many different types of plastics are those packages made out of? So it might be kind of an interesting thing to have students think about all of those different products.
Good. All right, you guys, so if you're ready, if you could go ahead and change or switch your book to ink chromatography. So that's the first page right after Unit 6, refining and processing. We're going to start to talk a little bit about with our students, how is it possible? So you've seen crude oil. Maybe you can get a sample of that. But, think in general of a darker substance that's pretty thick, liquid. And ask your students, how can we separate great products from this substance so that we can use them for many different, just many different things in our home and in our lifestyle? You can kind of look around your classroom and say, hey, what are some things that are in here that are produced by crude oil in the refining process? And help your students understand that refining process is what we do to help break off hydrocarbons so that we could use them for things like gasoline or natural gas in our home, or some of the materials or synthetic textiles that we're wearing on our bodies, or storage containers, all kinds of things that we use in our daily lives. So to help them get started about thinking about how one substance can actually be composed of multiple substances, we're going to do an ink chromatography lesson. Okay, so the materials that you will need are some water and just a pinch of salt, if you have some salt. This is just a solution that will allow those colors to help separate. It's really a carrier solution, so it's just a very low concentration of salt. then you can use really any kind of paper. I know the lesson calls for either coffee paper, filter paper, or chromatography paper. And I believe that in your containers, sure, that's okay. In your containers, you got some round chromatography papers, okay? So I know that you guys are asking for some time to prep the salt water. That's okay, but I'm going to continue to just talk a little bit. So all you have to do is pour some water in a cup and put a pinch of salt in it. You can also measure it out, which are good skills for your students in their classroom, good measuring and calculating skills. But for us today, I just put a pinch of salt in a beaker full of about 300 milliliters of water. Another piece of this lab that you'll have to do, if you've not yet done it, is to go ahead and cut out your chromatography piece of paper. So if you have a round piece of paper like this, you can go ahead and measure it 6 centimeters by 8 centimeters if you like to. But what I'm going to tell you is I've already done that. So everybody see this? And really all you're doing is just cutting off the edges. So if it helps you just a little bit for today's exercise, you could cut off the edges. Measure out 6 centimeters across and go ahead and cut them out. If you have coffee filter papers, I've gone ahead and drawn out 2 squares, 6 by 8 centimeters. So you could prep that with your students. You could definitely draw those out for them ahead of time or cut those out for them ahead of time. But you don't have to be necessarily limited to this small size. You could use a bigger piece of paper also. And if you're in the classroom and you have completely forgotten about coffee filters and chromatography papers, which I have done, you can use office paper and it still works, but it does take a little bit longer period of time, but it does work. Okay, so there's lots of options that are available to you, and we're going to show those to you quickly. So once you have your piece of paper of choice in front of you, I'm going to help problem solve a couple of things. If you're using your chromatography paper and you've cut your strips off, I would also suggest that you cut a flat bottom. So kind of go from point to point there so that your paper is flat on the bottom. Okay, this will help to make sure that the water moves up that at the same speed across the entire piece of paper. If you have a rounded bottom, it'll move up a little faster on these sides than this, and it could cause your colors to become diagonal on your paper. Okay, and once you get your paper cut, go ahead and divide it into 6 equal sections. I just do that by folding it into thirds first. But you can also measure it with your ruler into 1 centimeter sections. So once you have it divided into 6 different sections, Jane, I'm going to let you do it on regular piece of paper, as I know you want to do, or on the coffee paper, whichever. Take a pencil.
We're doing it the long side.
Yes, ma'am. And draw a line across the bottom and put some initials for red, orange, yellow, green, blue, and then brown.
It's not that way. I always have trouble with these things.
It's all right. It's a good visual exercise for students to be thinking about, again, how to fold a piece of paper into 6 equal parts, or using your ruler to measure out those centimeters. They're both good skills to learn. So again, with my accordion file, I've gone ahead and used a ruler and I've drawn a line across the bottom. And then I've just put initials for my rainbow colors: red, orange, yellow, green, blue, and then brown. And the reason we chose to use brown is because brown, as a more complex color, actually has more ability to separate into different indistinct parts than some of the primary colors, for example. Okay, once I do that, I'm going to go ahead and take my markers. I think I'm missing red. And that's okay. Just put a tiny little dot above it, okay? You don't want it to go across your lines or it might move into another zone. So I'm putting a dot that's like this. It fills up about half of the space. Thank you very much. And because we're using washable markers that are easily broken apart, it will help these colors to move a little bit faster up your chromatography paper. Okay, so when you're ready, kind of hold your paper up, and it should look something like this. You see that, Florian? Okay, nice. I see some great examples right now. Awesome. Some people are definitely better at making circles than I am, and I applaud you, just so you know. That is a skill. Great. Okay, I see some people are still working on their chromatography strips, and please remember, any paper that is permeable to water will work. There are some papers that are made with, and this is going back to our previous unit, greater porosity and permeability so that the water will move more quickly through them. So this is another great way to tie back to our previous unit where we discussed porosity and permeability, just in other materials, okay? All right, so once we're done with that, you guys were also given some cups. You should have a plastic cup. There's two little notches down here at the bottom. 1 centimeter is about 1.5 of those, okay? And the directions suggest that you pour about 1 centimeter or less of your solution into your cup. So I'm gonna go ahead and do that. Looks like I've got a... You can write salt solution at the bottom of your cup for your students. It's always best to put it on a flat surface first, just so that you know you're getting the right amount. Jane, I'm gonna let you do that to your cup. We got a friend in there, I see.
Oh, a little floaty.
Yeah, a little floaty. Now, the reason why we chose this 6x8 design is because it easily fits into your cup, okay? If you have a bigger carrier of water, so if you have a bigger beaker or something, you could make your chromatography paper bigger, okay, if that's easier for your students. But all we'll do now is we'll then go ahead and put our paper into our solution and let it sit there and watch it happen, watch it work. Talk to your students about what do you think is going to happen. You know, there's lots of water properties, even just right now as science teachers, we can talk about why is the water moving up the paper? Why is it moving against gravity? Okay, what are the properties of the paper that allow that water to move up? And what are those, is it like 9 properties of water? I have to refresh my brain here, that allow that water to move up. So there's capillary action as it moves from pore space to pore space, and it moves up that paper product. And what do they begin to see as the water comes in contact with the colors? So are you guys beginning to see some action on your paper? All right, so which color do you think will move the furthest? So, and what is the property of that color that allows it to move further than another color? Those are all good questions that you can feel free anytime to put the answer in the chat, because I know you guys know the answers. Oh, that's great. So let's just look at my sample that we have there. Right now it's beautiful. It almost looks like some hearts with those colors as they begin to move up the paper. And so what students will start to see is, first of all, do you think that all of the color will even remain in those bottom spots where the initial circle was drawn?
So asking them to make some predictions.
Mm-hmm. Mm-hmm. Good. I wonder, do we have any art teachers in our, they would probably know more about colors than I do when it comes to their particular properties. But you could, if students have, know about primary colors, they could certainly, talk about yellow. Yellow as a primary color is not going to really separate or break apart like the other colors that you would see there. So for example, your browns or your greens or your oranges. And then when you're looking at your red and your orange, or excuse me, yellow, you can also discuss, which one of those will move further and what property allows some of those colors to move at a faster rate or move faster up that paper, further away from the source of the water. So your students should be able to have some good conversation in their groups or by themselves, if they're doing this by themselves right now. And if you can't come in contact with your students and you're doing this virtually, look at what a great job our camera is doing right now. The students can still have a good conversation with you virtually online as you guys are talking about what's happening right now. You could even have them make predictions about the different types of paper that you're using. So if I use a paper that has higher permeability than another paper, will I get a different result? Okay, and they will have to talk through that and really help you to understand why or why not that is. Okay, so I'm going to allow this to continue to move up. So that's great. Look at
Yeah,
Jane's paper.
that's totally different.
Well, if you're
Using too much water can be a problem.
Mhm.
And especially if you don't have, and like mine, I just stuck mine right in the water.
Mhm.
If you have a little bit too much over your line, then yeah, that
But-
can be a problem.
And I'm going to help you problem solve that just a little bit. We do want to make sure that our students get the paper in the water, but the water has to be below the colors. Okay, so so that being said, and we also want to provide enough water that it can easily go up the entire piece of paper. So a great suggestion to help with it kind of bending or something like that is to just go ahead and use a pencil like this one and put a little tape on it. You can roll it around your pencil and you can go ahead and pick up a piece of, whatever you have, the very edge, and then you can roll it as much or as little as you need to make sure that that is just sitting upright inside your cup like this. So since this is still a little tall, I would want to roll it up a little bit more. And that'll stand perfectly up and it won't bend, and so your color should go straight up your paper and not get wonky on you.
Yeah, that is one of the
Let me show you
little
how.
bit of a challenge. Yeah,
Yes.
is when you use round cups,
Mhm.
the paper gets wet and it sticks to the side, so it starts to bend.
Yeah.
So you can
And
see.
Florian, can you show them these? So look at this. I first put this in the cup with a rounded bottom, and look what happened. It tipped, and then all the water went this way. So these colors began to blend over. So I remedied that, and I went ahead and cut my bottom flat. And then notice how far up on this dried piece of chromatography paper these colors went. There's no evidence of the colors at all down here below where they were. So as you look up here, you can easily see how far those colors are traveling. You can see the red and the purples separating out from your blues. Over here in this brown, you see the lighter colors like yellow and reds before you see your blues up here at the top. And even over here in this red, you see a little bit of pigment that's beginning to separate out from there as well as with this orange. So the student should see some good variation and separation of pigments in those colors. And that was with the chromatography paper.
Oh, that's what I was going to ask you.
Yeah, this is an example of using, can you see this really good? The coffee filter. So this, of course, has high porosity and permeability, but notice because there's a little less material here, the colors are not as easily seen. They can get lost in the water themselves because they're not adhering to the paper, and they don't just like kind of pull apart quite as easily. And then I wanted to show you that last sample just in case you have to be like me and use that office paper. Here's an example of office paper. So look at this. In the office paper, what's really interesting is that the water traveled further on the far side with the brown. So did those colors break apart? Were they lighter and better able to travel away from that solution as they move further up? These are all really great questions for you to talk to your students about, but this paper was set in at the same time. Okay, let's look back to my paper here. Can you see that okay? So my paper is about 2/3 of the way up, and you can really start to see some good coloration there. The students can see the green distinctly pull away some of the blue at the top and some of the yellows at the bottom.
Yeah.
The same with the orange. You start to really see that beautiful red towards the top. It almost looks like a perfect flame upside down, really. And then over on the browns, you begin to see some again of the blues and the greens. So what I have noticed is that it seems like the blues and some of those greens must have lighter properties, and they're better able to travel up that paper further away from their origin. That's just my observation. What observations do you guys have that you can put in your chat? Ah, that's a good question. Do you have to use washable markers? You don't have to use washable markers. You can use any inks, but washable markers are made with a different base than more permanent based markers. And so they're just a little bit easier to travel with the water. They get picked up by the water a little bit more quickly, and they move through that medium faster.
Yeah, if you use a Sharpie marker or
Hmm.
something like that, you may have to use acetone to
Hmm.
actually separate it. And acetone is not something you might want your students to be in contact with. So
Yeah, that would be.
this washable with the salt water seems to work pretty well to
Mhm.
show that separation. And again, just to connect it back to why would we do this is to start thinking about how do we get different things out of this crude oil that goes to a
Mhm.
refinery. So this is just one example of a way that materials, inks, and color pigments can be separated, just like we can separate parts out of that crude oil.
Yeah, a lot of inks specifically have an oil base to them
Hmm.
to help them keep their permanency on on pieces of paper and other
Exactly.
products. So, there is a lot of oil that is in those elements, and so this is just a really cool way to show students how one element can be made up of more than one thing, and they can be broken apart.
Yeah, and black is also another
Hmm.
interesting color you can use to see if it will separate along a gradient as well.
Yeah. So when your water, to finish this activity up, when your water does get to the top of your paper, you'd want to pull it out and let it dry. If you let it sit in there, it'll actually creep out of your paper and go somewhere else, which is also pretty cool. You could have like, what happened to the disappearing ink, Mrs. Bryan? So you could have that question too, but because of that capillary action of the water and adhesion and stuff, it'll actually creep completely out of your paper if you're not careful. So just don't lose your ink along the way. Okay, is there any questions about this particular activity? Let us know as we're kind of setting up for the next activity. The next activity, you just need to,
Switch or
yeah, well, I think we're just gonna, it's just right here.
no, I mean,
Do
do we
you
need
want
to
to?
move around or
No, that's a, oh, you mean in front of the table? I don't think so.
no, never mind. Go ahead.
Okay, I was gonna make you dance, Jane.
No.
So anyways, the next activity doesn't really require anything other than you to turn to the page of the lesson. So when you get cleaned up, take a moment. We're gonna go ahead and move on to classroom cracking. And then after that activity, we'll take a break.
We're not going to do this.
That's the last activity. We're going to do it after our break.
Okay.
Okay, so just kind of give me the thumbs up when you guys are ready. You might be, thinking a little bit about that ink activity and have some questions later on. You can always put those in the chat. But remember, it's important to let your papers completely dry before you allow them to touch anything, because that ink is still mobile when it's wet.
And it's a good opportunity
Mhm.
perhaps to, try different brands.
Sure.
Different brands of markers, different whether Crayola does the same thing as Rose Art, and what pigments are they using. So it's kind of an interesting mystery to have your students solve as well.
Yeah, it's interesting. We do an activity in the geology curriculum where you do have to use dye by a very specific company
Hmm.
to get the end result, which is funny. So the density result, you want to move it over here? Awesome.
Out of the way.
Sure. So this is an interesting question. What would it move more quickly if we were to wet the entire paper at one time? Well, the problem with that is your color will just go in all directions. To get it to go gradually up and to separate the way that we need it to, you have to have it be accessible only from the bottom so that the water is moving only in one direction. Okay, and remember that ink is broken apart by that leading edge of the water, and it travels with the force of that water as it moves up your paper. And so if you break up that force, you won't get the end result, but you can try it. That's a great question for students.
Hmm.
They should certainly make a prediction, and then they can attempt it, and then they can explain it to you like, oh, why didn't that work, Mrs. Bryan? Okay. well, I think that's a good point. We have a question about if you were to dip your paper up and down like a tea bag. So let's just try it. There's nothing like the present. I'm only going to put one color on here, guys. We'll see what happens. You can make a prediction right now. What's going to work? Should we put like blue, something that we know will break apart, do you think, or green?
There's enough water.
Yeah, I think so. We'll do orange and say green, because we know we'll get a reaction out of those. All right, here we go. I'm going to dip it up and down like a tea bag. But the problem with that is you might need more water. Should we do that? Add more water? Remember, if you add too much water, it'll go over the level of your ink. And again, it will take it out of an upward direction. Can you see this okay, Florian? Okay. So I'm going to dip it up and down like a tea bag. What I see is that the color is moving downward with the force of water versus up in the direction that we like. There you go. Can you see that okay? Right there. I'll leave it in there.
Yeah, just leave it in there and see what happens. See if any of it does move the other way.
Good. So instead of the ink moving upwards, up the vertical piece of paper, it's actually moving down because you're creating that force. As you lift it up, you're allowing that water to go down. So it's kind of moving more in that direction. Now after I've set it in the cup, we'll see what happens.
It's just kind of drowning.
Now it's drowning. The color is drowning. Oh no.
Because we have so much water in there.
Yeah, well, that's going to happen. Eventually the color's just going to disappear in the water, I think. All right, you guys, well, if you can go ahead and turn it to your next page, which is classroom cracking. We have one more activity before a quick break. I really, really love this activity. I'm going to be honest with you. Although it does make you kind of get a little bit out of your happy space and get a little giggly with your kids. So I hope that's okay. So
they'll like you more for it.
Yes, for sure. So this activity, to be completely honest with you, was actually made in non-COVID conditions for students who could touch each other. But that's not the case right now. So you could have them as socially distanced as you need to do. They could also just do it at home, you know, however you want to do it. So there's some differentiation, which for our current climate needs to be addressed. But in future times, when we're all allowed to be back to somewhat of a normal type classroom where students are allowed to hold hands, just keep in mind this activity was made to go ahead and have students come together, okay, and then break apart so that they would simulate the cracking of a hydrocarbon off from a longer chain. So just in reference as background, remember we talked about crude oil being a long chain of hydrocarbons. So if we break apart the word hydrocarbons, that really brings up two elements that we would discuss, which is both carbon and hydrogen, okay? Now, depending upon the level of your students, they may know a little bit about molecular, you know, how things bond with one another or how they form, and they may not, because that's more of an advanced skill. I think it's 5th or 6th grade. But just the idea that they break apart and that's how they separate so that we could have them due to increased energy is really what we're trying to get across here. So let me just kind of go over that. What we've given you for this activity that you see are some cards. Okay, so they're actually, as you turn the page, you'll see those there. There's 6 different what we call cracking cards. And those cracking cards each have a different product on them. So the first one is natural gas. There's a few things that are a part of this that you can see on your card. There's a stove, so they get a feel for how would I use natural gas. There is also some things they can look at: the name, a cracking temperature, which is actually 0 degrees Celsius, the molecule size, which is only 1 carbon. So it's a very small molecule, and what we use those things for. So some common uses for natural gas are cooking and heating, for example. And then finally, there's a thermometer on here, so students can see that the temperature is also very low. Okay, so there's a couple of different things that we have going on. When you do this lesson, we suggest that you use some form of music, if you can, to help simulate energy increases. Okay, and just remember, when we're thinking about hydrocarbons and we're thinking about the refining process, a lot of different hydrocarbons are actually cracked off or separated from the original product by using thermal energy. Okay, so as we increase our thermal energy, so as the temperature goes up, we get more energy, which then causes those hydrocarbons to crack off or break off. Okay, so in looking at this lesson, let's look at the chart that you see just up here in the top right corner. Okay, so I'll hold it up. Yep, right here on this corner. Okay, and see that there's 5 different products that we're going to consider. And let's just review that chart quickly together. So you see that on the left side, there are some temperatures. Okay, oops, sorry. Yeah, so you can see that better.
I don't know. Does it
Maybe
work
it's,
if I put
yeah,
it that way?
I'm not
Is
sure.
that better?
Yeah, that's fine. Yep.
Okay, and then the next thing is motion to correlate with the temperature. So we have the students moving in motion to help correlate with the increase of temperature. So we're going to move really slow at first when the temperature is very low, and you could have music moving that is like slow music. So you're humming a song very slowly.
At a very
Okay.
slow tempo.
Yes, so a lower tempo. And then, you know, when the teacher indicates, students would crack off, and then they will go and pick up that particular product card that would have the number of molecules that you're suggesting in the chart. Okay, so there's a couple of different things going on. You'll be given some thermometer cards, so you could hold up a thermometer and the students can see a low temperature. They're also going to feel low motion. Okay, you're going to talk about the number of hydrocarbons, so the number of carbons in the molecule, so that they could find the card later on and talk about it and report back to the class. And they're going to hear some music that will correlate with everything to help with this kinesthetic exercise. Okay, so we're going to get started, I think. Are we ready? So let's just read this together. Sorry, it's upside down, so I'm going to take this back here. Okay, here we go. So it says here at 0 degrees Celsius, okay, we are going to be able to crack off natural gas, which is definitely a product that we use often every day. Perhaps even at your school, your buses are powered by natural gas, for example. Okay, and because it is a very small hydrocarbon, okay, so just one carbon molecule, it doesn't require very much energy to break off. As a matter of fact, at a normal temperature, it'll go immediately up into the air. Okay, and so that's actually one reason why we put I guess a smell to it, right? We add so that you are more aware of it because it's odorless. Okay, so that being said, as you're looking there, we could be humming a song. So students are holding hands in one big long hydrocarbon in your entire classroom, or in this instance of social distancing, they're thinking about holding hands. And you're swaying very slowly because you have very little energy. And so you're talking to your students about, hey, you know, how would we break this product off from this big long chain? It requires very little energy. I don't even have to turn really the thermostat up, you know, out there in the refining tower. And so you can talk, you could even hum a song. You could, what were we going to do? The chicken song? The only song we could think about was the chicken dance. So if you were humming the chicken dance, it would be like, na, na, na. I mean, it would be very slow tempo, you know, so the students could assimilate that low tempo with the movement of their bodies. And then the teacher would say, okay, crack. And so the students she would say, or he would say, take 2 off, and they would go and they would find the product card, which in this instance is natural gas. And they would report back to the class. Okay, they would talk about what is the temperature that's needed to crack off. Okay, what are some uses of natural gas in our everyday lives, right? As well as how many carbons does it have? So if it's just one carbon, you know, so then in a big group of students, perhaps that's 2 students that make that molecule and they go over and they pick that up. Or you could have it be 1. You could have it be 5 students if you're thinking of your carbon and your 4 hydrogens. So it's really your differentiation in your classroom. Okay, so that's 1. And you want to make it fun. So it's kind of like musical chairs if you add your music to it, right? So when the music stops, they know to crack, and then they go and they find their product card, okay, and they report back. So the next one is gasoline. So that's also a product we use all the time. And so with gasoline, it's actually 7 carbons. So that's a small hydrocarbon that we use, but it does take a big increase in temperature, so 150 to 200 degrees Celsius. So if before we were just very gently, you know, being big trees in the wind, however you want to say it. I'm a high school teacher, so this is difficult for me. I just want you to know. You know, here it says arm swaying, So we're swaying a little bit more because I'm excited. I'm 150 degrees Celsius or 200 degrees
It's a little
Celsius,
warm in
and I'm
here.
starting to stomp my feet, you know. So there you go. So you guys get it. So we need more energy to move my body like this. And as we move like this, all of a sudden the music stops. So the chicken dance goes da 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 da. And then we go and we get our product card and we report back about the uses in our classroom. Thank you. All right, so the next product that we have is about wiggling. And I want you to think about this. So this is diesel fuel and jet fuel. So this is 200 to 350 degrees. So
we're a lot warmer now.
So first we're just like this, and then we're stomping, and now we're jiggling. You know, we're wiggly, right? So I need more energy. And so if I'm using up, I can't dance too much or I won't have enough for the end. So if I'm wiggling right now, then that is the next product. And so the chicken dance gets a little faster, da 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 da, and then they crack off. And so what we really want them to correlate, you know, with all of these activities is, oh my gosh,
it takes more energy.
Takes more energy for a bigger hydrocarbon. So it takes a lot more energy to get that bigger hydrocarbon moving and then breaking off from the large hydrocarbon.
And the best part of this activity is you won't even have to demonstrate. Okay, that would be the best part of
They'll
the
be wiggling all
that
in
they
there.
will just take it from there. You probably won't even have to say anything else. Okay, music's gonna get faster.
Yeah.
Now we're getting at a 15, you know, or how many hydrocarbons are in the
16.
next one for candles?
Yeah,
right?
anywhere from 16 to 60. So, you know,
So, yeah.
So your cracking cards might give you a variation, and that's okay because they're really representing these many products down here that crack off within this particular range. Okay, so you could have, like right here, we have 15 kids breaking off. So wow, this is a lot bigger, and it takes a lot more energy to move us across the classroom and pick up this card and then report back on it. So even like having the kids poll each other, they can also help to correlate that with the amount of energy that's needed. Okay, and I know you guys all want us to dance in place here, but road tar, okay, Jane is like this, woo, woo, woo. Okay, so road tar is really one of the heaviest substances that is a part of crude oil. And because it is so heavy, so dense, because everything else is cracked off before that, just remember this takes a tremendous amount of energy to get to. Okay, and so, you know, the whole class would have to move across to go find this particular product card, wiggling and dancing the entire time. Make them wiggle and dance the entire time to get to this product card so that they can really understand how energy is necessary and how we use that energy to help separate, you know, those materials. Okay, so that's classroom cracking. So I hope you enjoyed it. We didn't do it justice, I'm afraid, but we had fun.
Okay.
Yeah. And so if you had music playing, which we couldn't coordinate today, and you know you're jiggling and your kids are having a good time and eventually they're allowed to touch each other, that's great. But if they're not, they're just socially distancing and dancing the whole way as they make their way to get their card. Okay? So the other thing I wanted to point out, and I apologize I didn't do this, but you also have this slide that's available to you. And so you can show them how these products crack off on this refining tower. So you'll see up here, natural gas is at the 0 degrees right up here. It takes very little thermal energy for that to crack off. And then as the temperature increases, because you're getting further down, you'll see other products that crack off. I'm trying to remember how many products they actually produce at a refining plant. It's like hundreds of products.
Yeah.
It's amazing the number of useful products that we get from crude oil that we use in our lives.
Not nearly this simplistic. So if
Yeah.
you look up refining, an image for
Yes.
refining, it's very complicated.
Yeah.
So we are fortunate to have scientists and folks who took that on as a career to figure out all of this. So we have all of the products that we do.
Yeah, absolutely. So one of the things that we want to make sure you're well aware is that we're waiting until after the post-test is done, which will be sent to you at about, I believe, 6:30 today. So take a look out and make sure.
Not 6:30 today.
Oh,
Tomorrow.
Okay, sorry, it'll be sent out tomorrow in the morning. So the post-test will come to you, and then at the beginning of next week, so about Monday, we're going to send out an additional email where you'll get the slide deck. You're going to get a connection to Ohio Standards for all the different lessons that you've seen today and yesterday or last week. You'll get just an email that'll be full of resources for you. But we like to go ahead and look at the chats that have come in the last 2 sessions and look at the post-test so that we can best answer everything in that follow-up email on Monday. Okay, so anything that you would like access to, please put it in the chat, and then we'll be able to really take a good look at that and make sure you get those materials the following week in an email. Okay, also, if you haven't gotten any emails from Sally Ewan about this and from Ujit, please put the proper email address in the chat for us so that we have that too. Yes, Lima does have a refinery plant. So, is there one, where's the other one in Ohio? There's also one up by Toledo, in Oregon, Ohio, there's a refinery plant of some kind because I've passed it several times.
Yeah, there's a natural gas burning electricity plant in Oregon, Ohio. So
we've seen two.
Yeah, that's been cool.
Yeah, there's some amazing things. And if your students have any interest in engineering, well, here's a place within this entire industry. There's just so many different applications. And on the UJEEP website, there is a great place where you can see videos of all the different possible careers that you can enter, and there are descriptions. They've done a fantastic job with different career sheets that you can use with your students as well. Okay.
Well, and keep in mind that these are pilot lessons, and we're really looking for feedback.
Yes.
So if there are things that after this is over and you think, hey, that's a great activity I can have my students do, and any feedback that you can give us from that activity, working with your own students, we'd really appreciate that, because that you guys are out there, you're in the trenches. So we'd really appreciate any feedback you can give about how to make it more useful, make the connection stronger, make it more address standards. We're willing to look at that feedback and try to make it so that they work for you.
Oh, absolutely. All right. Well, right now we're going to give you a break after you do the poll results. Okay. So take the poll results, and then we're going to take a break. My goodness, it says 5:12. So we're going to come back. We have 2 more activities, guys. So how about we take just a 5-minute break?
Yeah.
5-minute break. So why don't we come back together at 5:20? Okay, 5:20, we'll come back together. Thank you, guys. Hey, guys, how are you? We're glad to have you back.
Oh, we're not ready for that slide yet. We have one more activity in this unit. So we're going to finish that up before we, before we move on.
Gotcha.
So, yeah.
So you should have your lesson book turned to Build a Hydrocarbon. That's the last lesson in Unit 6, Refining and Processing. So when you're ready, give us a thumbs up. Awesome. We doing okay? All right, so for this lesson, you should have a bag in front of you that is full of marshmallows and toothpicks. How are we doing? And it would be called Build a Hydrocarbon. Good. So the reason I see,
okay.
That's something I just could never do. I could never eat marshmallows. I mean, my husband, he'll pop them and, I just can't do it. All right, moving on. So the reason you have 2 different size marshmallows is because they actually represent different size elements, I should say. So we're going to build molecules, okay, with these, and the big marshmallows are going to be carbon, because carbon is a large enough element that it can have 4 different attachments, okay? So it can bond with 4 different elements. And then the small marshmallows are hydrogen atoms, okay? So that carbon atom can then bond with up to 4 hydrogen atoms, or a different variety based upon, whatever the size of your hydrocarbon is, okay? So in this particular activity, because we know it's a little bit more complex of an activity, we have different, as you can see, hydrocarbons here on the left side in your chart. And we've given you an example of one up here. Okay, so in the top right of your activity, you'll see an example of ethane, okay, which is a 2-carbon hydrocarbon. So a 2-carbon molecule, okay, with 6 hydrogen atoms attached. Okay, So the reason why we chose to give that sample instead of methane, which would be 1 carbon, I'm going to make a methane really quick. I know I couldn't resist, sorry. Okay. Which would be just 1 carbon atom attached to 4 hydrogens. And there's different ways you guys can do this. I'm going to just show you this really quickly. So I choose to put my toothpick all the way through my marshmallow. Now it'll save you toothpicks, but also make it a little bit less wobbly. Okay, you can do that, or you can use 1 toothpick per hydrogen also. So it's really your comfort level. But notice that I've just got 1 toothpick that goes all the way through, and it's got 2 hydrogen atoms attached to it. So as I make up methane, I'm going to show you what the kids are going to have to think through here. Remember in our last activity, what we did was we took these hydrocarbons and we actually broke them off. We cracked them off, a large hydrocarbon. So here what we're doing is we're showing the students what those small hydrocarbons look like, using some fun with marshmallows and toothpicks. Okay, so I don't know if you can see this little marshmallow guy, Florian, but this is methane. So see how small this molecule is, this particular hydrocarbon? Remember, each carbon atom can attach with 4 different atoms. So notice that it's attached to hydrogen here to help fill out its shell, okay? So when students see this particular one, they think, oh, okay, 4 hydrogen atoms attached, that makes sense to me. But when I add another carbon, where do I put that carbon? So the reason we have the sample of the ethane up here is so students can see that the carbon atom can attach to another carbon atom. Okay, so Jane has made a marshmallow example of the diagram that you see in your book. So some of the questions that we can ask students is, okay, how many hydrogen atoms are necessary to complete that hydrocarbon? So it's really kind of the opposite of classroom cracking. So what they're really doing is they're physically building these hydrocarbons that we just talked about in the classroom cracking activity. So they can see that this smaller hydrocarbon would require less energy to move, so less thermal energy than this larger hydrocarbon that's next to it. But we could add them all together and make an even larger hydrocarbon too, like that. Okay, so what we're asking the students to do in their groups with this particular activity, build a hydrocarbon, is to have them think through the process. How many carbons would it take to make heptane, for example? You guys see that it's 7 carbons. So they can go ahead and predict how many hydrogens they need to finish that hydrocarbon out. They can do what Jane's doing right now. She's laying out 7 different carbon atoms. And then she needs to make sure that each of those carbon atoms has 4 different atoms attached to it. So she's going to begin to build heptane for us. But for younger students, this is probably a pretty tough activity. So we want to talk to them a little bit about, why are we adding different atoms? So as they grow older and you're in more of a 6th grade level, you can talk a little bit about electrons, as far as filling out shells. And
it'd be easier to use the longer one.
Yeah. Did you have a smaller one?
Yeah,
Gotcha.
I bent them and
Oh, gotcha.
so they didn't stick out so
Yeah.
far.
But it's also a good way for students to project and build models. And so they can also see how a large hydrocarbon can then be broken down into smaller hydrocarbons too. So this is just a really great lesson to showcase how you can have one big chain that can be broken up. And then you can talk about what are similar properties that all these hydrocarbons have. So whether it's a 1 carbon hydrocarbon or a 3 carbon hydrocarbon, do they have anything that is similar? Do they have something that is different? And they can begin to talk about those different properties of the atoms that are a part of that. Uh-oh, you're getting some chubby marshmallows.
Longer toothpicks.
Yep. You're getting some chubbies. Yep. You can also refer back to your cracking cards that you see in your previous lesson. And that will help students to understand how many carbons are a part of each product and what is the energy that's necessary to crack those off. Jane's just having fun right now,
I
you
am.
guys,
I
with
am.
marshmallows and toothpicks, and so will your students. Just a few words of caution. You might want to choose rounded toothpicks,
Yeah.
depending upon the age group that you're with. You can even use, and what works really great are popsicle sticks or coffee stirs. All of those things work well.
Let's
Some.
just make the propane. Get a little tired.
All right, all right. Okay, and you can use other materials. I know some people use styrofoam balls and things like that, but some of the things we really want to think about is how are carbon and hydrogen different as far as the type of atoms that they are. Why is it that carbon allows for more attachments than hydrogen does, as hydrogen can only attach to one different atom, for example. There you go. That's a very cute propane molecule that you have going on there. So because Jane used the one toothpick, you can see that even though she has more carbons in that particular hydrocarbon, it actually looks a little smaller, which is interesting too. A few other things to think about with this particular activity is the stale, like the longer your marshmallows sit out in the air and they become a little tough on the outside, they're stale, the easier it is for them to stick to your toothpicks and not roll around on you too.
Yeah, and then you don't get quite so sticky.
As well. Yep. And ours have set out for a while.
Yeah,
so you're still getting that sugar will cling to you no matter what, I'm afraid. Good. So this is just another way to model different molecules that you can find in oil and natural gas. And so, it's also showing students that, gosh, we've only got up to heptane, right? But let's go back to our cracking cars. Where was that tar at? Oh my gosh, 80 plus carbons.
So you're building for a long time.
Challenge them to make an 80 carbon molecule or hydrocarbon. That would be fantastic. Now you probably would have to have it all along, I don't know, a shelf or something, right? Countertop for sure. But the students will giggle and have so much fun. Okay, and then after they've made their road tar, have them crack it apart and make different molecules as well. So they really understand how how a smaller molecule requires less energy to crack off. Okay, and so that's is something that's really useful, and it really helps them to understand the properties of these different hydrocarbons. And you can also ask them, hey, if they do some research, what's a 10 carbon hydrocarbon? They could do some research and report back to your class and talk about what that product is and how you use it in your everyday lives. Okay.
Well, and you can also ask them if there's a pattern.
Mm-hmm.
So for instance, methane, we said, has number of, this should say hydrogen.
Oh, it does. You're right. Thanks. See?
So it should, number of carbons, methane we said is 1, but how many hydrogens are there? 4, right?
Yep.
Well, if you go down the list, then let's say for ethane, we've added in that you need 6 hydrogens. Yep. But what about butane? How many do you need for butane?
So, yep. So like here's a molecule of butane right here, so you could just count. Oh, yep, you're right. Sorry, I forgot to take that off. You're right.
So yeah, we gotta be careful about the number of carbons.
Yep. So what I've always done when I think about hydrocarbons is I just take the number of carbons, multiply it by 2, and add 2. So if it's 2 carbons, you multiply it by 2, you get 4, plus 2 is 6. So if it's butane, butane is 3 carbons. 3 carbons times 2 is 6, plus 2 is 8. So that's just a quick rule of thumb to help you create a hydrocarbon as you're moving down. So if you had an 80,
so you had 8 there,
yep.
And then you had 10 for propane, you could then predict what if you had a 5 carbon, how many would that be? So you can, weave in your math skills here as well.
Yep, absolutely.
Looking for patterns.
Looking for those patterns. That's good. Okay, great. All right, we're going to clean up a little bit and shove our marshmallows to the side. I see that you guys have already taken the poll. So we're going to move on, you guys, because of time, into Unit 7. Okay, our last 7 is petrochemicals and products. And we're going to have a little bit of fun making some polymers. So really, as we kind of reflect back on today, we've seen in the transporting how we are being efficient at producing crude oil and natural gas. And then we're moving into refining and processing, so really helping students to understand what makes up crude oil and the products that come from that. And now we're going to move into actually building one in a different way. So we went from marshmallows to some more fun stuff where they'll see chemical reactions, which is always a hit.
So the slide that was just up there gives a little bit of background, if we can flip through to the next one. So we had petrochemicals and products. That's this unit. That's what it's called. Basically, it's all about what do we get from all of that work that has gone into the biogenesis and then the migration of it and the finding of it. And now we've produced it and it's at the refinery. What do we get out of it after that? And so you can have students, like Heather mentioned even before, look around the classroom and find out what are the things that have some type of oil or natural gas product. So even the ink on their paper potentially could come from carbon black. Or the ink in their pens, depending on what kind of pens they have. Most of those products come from petroleum. So if we go to the next slide, basically, this is all that idea about the processing. So how did we get here? Who brought us here? Well, this is a whole group of study called petrochemistry. So we have petrochemical engineers who work on creating new products using these different polymers. And so this industry obviously gets its feedstock from those refineries. So a refinery isn't only just putting out jet fuel and gasoline and tar, but some of those products then are moved on to another place where they actually are processed into the plastic wraps and the different plastic materials that we have around our home that house our television screens and all of that. Obviously, they become very specialized and they include all kinds of things. So not just even plastics, but thinking about soap and thinking about fibers for clothes. Heather even mentioned that earlier. Paints. A lot of our paints have petrochemical products in them, and aspirin, antibiotics. A lot of our medicines have coatings that make it easier to swallow or help to release it in your system. So those kinds of things are really what we're talking about in this unit. And so there's really a wide open area that you could have your kids do experiments on.
Good. I think that's a good question. So we did have a question about, is one fuel more environmentally friendly than others? I think if you remember at our beginning of our conversation and back to the pre-test video that you saw with Kennedy, we need all fuels because we are really energy hungry, very selfishly kind of, like driven people. We had a conversation about this earlier. So what we're finding is that gasoline and diesel fuel and now natural gas is powering a lot of vehicles, and natural gas is actually very friendly, as far as the compression of that and the use in vehicles, as well as its efficiency in vehicles. But we cannot do it on its own. So there are also gasohol blends. Of course, if you go to the pump, there's a 10% blend right now with ethanol products to help boost octane. But that's just 10% of a fuel that we use in our cars every day. And so I think that what we're finding is that we are definitely making sure that we are utilizing every resource that's available to us as well as we possibly can.
Well, and even those biofuels are actually hydrocarbons. So it's just that hydrocarbon might have been produced at a different rate in a shorter period of time in a plant rather than across long periods of time in the ground. So it's the same process as a hydrocarbon, and we're processing those hydrocarbons in multiple different ways.
I need some water.
You need some water.
Yeah, keep talking.
So what we're going to do next is the polymer putty activity. So if you can turn to the next page.
Yep, I apologize. I needed to get a little bit of water. So for this activity, you were sent in your bags some borax. So we're just using the teacher size version here, as well as some glue. So if you have some water, that would be great. Sorry about that. Cornstarch and dish soap. Okay, and then you just have a beaker to help you measure some supplies out. You'll be getting more of these products that will be coming to you, excluding the borax. You should have enough borax there to make 1,000,000 bouncy balls, just so you know. But you'll need some materials like your plastic spoon. We gave you some Dixie cups, as well as just a way to measure. Okay, but if you don't feel like measuring out 5 milliliters, just remember it's really a 1-to-1 ratio right now. So you can think about that too as you're getting set up here. So when you're ready, give me a thumbs up. Okay, I don't want to rush anybody. I see there's still a few people moving around.
Getting water. That's good.
Yep. So all the slides that you guys have seen today, they will all come to you as a PDF in an email. So it'll be a PDF that you can actually use and show to your students as well, because that's what we're actually using as a PDF. And so you would just forward one slide at a time. So you'll have access to all of that. And actually, if you go under educational materials on Ujib, a lot of the slides that you've seen, a lot of the images, the graphics, we've pulled from there too. Okay, if we're ready, we're going to get started, okay? So this first part, as we're building polymers, you guys, we're doing some chemical reactions. We are utilizing borax, and even though borax is not the worst chemical I've seen, we're just going to ask you guys to do it as a teacher demonstration. You could choose to use gloves if you want. I'm not worried about it, but you know, borax is an agent that helps to increase reactions. So for that, you know, being said, yep, it's a little bit of a catalyst. Typically, it's utilized in solvents, so cleaning agents. And so as you can see here, this is just something that we'd like for you to do with your students to help them to begin to think about how two different products come together to create a polymer. So a polymer, of course, is what, you guys? You have any answers there in the chat session? What's the difference between a molecule and a polymer? I can't yet. Shelley, you're going to have to tell me. Okay. And part of this activity really is that students in elementary grades can begin to think of how can we combine products together to create a polymer so that we can also look at things like states of matter. So, you know, when we're thinking about Newtonian substances and then non-Newtonian substances, part of this lesson will begin to ask students to think about what states of matter do you observe as well. Okay.
Any guesses about a polymer?
Oh, that's true too. Yeah. Mm-hmm. Good.
And they're repeating.
Yes.
So in a polymer, you know, we talked about hydrocarbons. Hydrocarbons can be thought of as somewhat of an example of a polymer, but not exactly, because what we're doing is we've broken those chains of hydrocarbons apart, and now we're reforming them into different polymer chains. And so we're adding potentially some oxygen or some other atoms in there to actually make that strong. So oftentimes our chemistry teacher would illustrate it by having kids link arms. And so when they were all linked together, they're much stronger than if it's just two of them that are linked together. So the longer the polymer chain, the more strength it has. So a lot of these polymers are designed for different uses.
Okay. All right, so as we're beginning to think about this activity, the first thing that we're going to ask you to do is dilute a little bit of glue. So in this activity, it's asking you to take 5 milliliters of water and 5 milliliters of glue. But again, because it is a 1-to-1 ratio, if you're worried about measuring right now,
This is 25 milliliters of water.
We're going to use the other water with
we're
borax.
doing the other water. Okay.
I have to think about that a little bit. We got a question about relation to 3D printing. Let me think about that just a little bit as we're moving on. I mean, I'm thinking about the material you would use for 3D printing.
Yeah, that all depends on the material that you use as your base to actually do the 3D printing.
A lot of that is, of course, derived from petroleum base. Okay, well, to begin this particular activity, let me think about that a little bit. I would just think it would be building upon each other with the same material. And so it's really not a polymer, it's just you're building upon it with the same material. Well, all right, so let me think about that. But today you want to take 5 mils of your glue. Oops, this is not coming out well. I'm gonna have to open it the old-fashioned way. Look at that, there's a stopper in there. Who knew?
That would be why.
Woohoo! Gosh, everything's Heather-proof these days. All right, so, and 5 mils of water and mix that up. Okay, and while that's happening, I'm gonna ask Jane to go ahead and do 20 mils of water. Okay, with 5 milliliters of borax, and do the same thing. So I'm just going to pour my glue right here in this cup because I have a lot of beakers up here with me today. So, and again, when you're measuring, of course, you should do it on the table, right? So you have a better, more accurate measurement. So just take the time to go ahead and mix up your solutions. Remember, one is 5 milliliters of water, 5 milliliters of table glue, Elmer's glue, school glue, whatever you call it.
Just trying to get all the chunks out of the borax.
And the other is diluting the borax solution. So that's 20 milliliters of water with about 5 milliliters of borax. You're not going to get all of the borax to dissolve. As a matter of fact, some might even stay chunky, but you want to try to suspend as much of that borax into that water solution as possible. I smell the glue. It reminds me of elementary days.
We didn't have liquid glue when I went to school.
You just had paste.
We had the
Were
paste.
you a paste licker?
I thought it smelled pretty good.
Oh.
No. There was no smelling of markers. I just really liked the glue.
The things
The
you learn
paste.
about the people that
Yep.
you work with. All right, so
This is ready
then
to go.
when she has that ready to go,
Yeah, I mean, I've spilled it all over, so I guess
we're
it's
going to
probably ready.
pour it into our glue mixture. Okay, and then I'm going to go ahead and mix that up.
Yep. You can
Oh,
see it
look,
quite a bit.
you can already see, I'm going to just put this out here for Florian to zoom in on as best he can, but you can already begin to see the polymers or the chains forming. Jane, I might let you take over because you're closer, if that's okay. So what you're seeing is that chemical reaction that's happening. Remember, borax is acting as a catalyst. And so it's almost like making cheese in a way, guys, where you start to
Feels like
see,
it, yeah.
you'll start to see those glue chains react a little bit differently, and they start to form a clump in there. So you want to keep mixing it together to the best of your ability. Okay, you're strengthening those chains the more that you mix it up, and that's really what's important here. So continue to mix it up as much as you
Put some more of
can.
that borax.
Yeah, for one, no, I think you're pretty good for 1 to 2 minutes. I mean, you can even use your fingers if you want, but just because we're utilizing borax, we just suggest, as teachers, you do this. If you have some higher level kids, you could allow them to do it with some gloves if you'd like. Look at that, go. If it's a little wet, then just take out your clump of polymer and put it in another container and continue to mix it and knead it. So if you want to put, you can, there's a little extra water in there, so maybe one of your solutions was exactly accurate, or you used too much of something. That way students can see that it's okay. Okay, you can actually go ahead and change your protocol there just a little bit to get the product that you're looking for. And hopefully over the course of this minute or two, you're having some fun because you're making a super ball, and super balls are always a hit, right guys? So think about the properties of the glue. Glue is stretchy. Before we put it in, it was obviously liquid, and we know it's a liquid because when we put it in a container, it fills that container, right? But now that we've added a borax solution, so a water-based solution, we're starting to see a really cool snot-like substance forming in my cup, literally. Oh, look at that, see? Yeah, she's always I like to play with this stuff, so I don't mind. And then you can put it in your hands and you can begin to knead it as well. And really what you're doing in this kneading process is just like kneading dough. You're building chains and helping to dry that out just a little bit. So you can go ahead and put it within your hand and you'll start to see a product that's forming that was definitely not there before. You want to play with the snot, or do you want me to play with it?
I can play with it if you have other things to do.
So really what we're hoping our students do is to look at the properties. So what were the individual properties of the elements that we put together? Were they solids? So borax was a solid. Were they liquids? Water and glue were liquids. But when we put them together, we get this chemical reaction that changes the product itself. And they can begin to think, okay, well, what property or states of matter does it have? Is it a gas, or possibly a liquid, or even a solid? Okay, or is it none of those things? Does it have properties of more than one state of matter? Is it sticking? Look at that. Yeah, it likes you. All right.
Very cool.
So, can we categorize it as one thing? And what prediction do you have as you continue to put that whole thing together? Will it change over time? Will it dry out? Okay, so some of the questions that we're going to ask our students in the process is, does it keep its own shape? So Jane kind of put it on her hand and it's starting to flatten out a little bit. Well, It's not keeping its own shape right now. It's starting to fill the shape of a container, which happens to be Jane's hand right now. Does it spread out? Can it be poured? Well, I don't know. Jane could try to tip it perhaps, and let's see if it's easily poured or if it falls in a glump. Or it just likes Jane and it stays right there on Jane's hand.
It's slowly
moving.
Yep.
Ooh, it is kind of an unusual thing. You could add color to it or glitter to make it more exciting too, I suppose. But as you're looking at this, you can see that it really is exhibiting over time, mostly the liquid state of matter. Okay, if you continue to work and knead your polymer, would it change? Will it become more salad-like, more bouncy ball-like over time? So those are some good questions for your students to think about and to describe the different properties of the polymer that we have made. Even as you're kneading it in your hand, you'll hear some different sounds like cracking, as you're going ahead, and Jane just ripped that thing apart, and then she's gonna put it back together. So allow your students to observe you as you manipulate this polymer, or if you feel comfortable with that, allowing the students to do that themselves. Okay, and this can help us lead into our next activity on the following page. So she's going to continue to go ahead and make some super balls. And students can even look at that and they can think, well, what would happen if I put less water in my product? So if instead of 20 milliliters of water to my borax, what if I put 10 milliliters of water to my borax? How would it change the final product? What reaction would I get? And students can begin to make predictions and then test those predictions as well based upon their observations that they're seeing. So really fun. And actually, if you continue to knead that thing, eventually you'll get it dry enough where it will make a super ball type consistency. And then they can even add different things later on. Oops, sorry. Okay, so our next one is a polymer that our students can easily make because the ingredients are a little bit more user-friendly.
How are we doing on time?
We're doing good. Oh,
Awesome.
I guess not. All right, we're gonna make this one quickly. We got about 10 minutes, guys. So I thought we were doing.
Like we've been.
All right, let me get on this clock. Okay, we're gonna get serious, you guys. Okay, here we go. So Jane's gonna do one and I'm gonna do the other. Okay, so in directions number 2, we're gonna use cornstarch, which is a polymer, and dish soap. Okay, and we're going to do one that has a combination of 45 milliliters of cornstarch to 30 milliliters of dish soap. Okay, so Jane's going to do that one. Whoops, sorry. Here you go. Here you go. Whatever you might need. Okay, and the next one in number 2 is 45 milliliters of cornstarch, but this time 23 milliliters of soap. So one product will have more dish soap, and the next product will have less dish soap. All right, so give us a minute to get going on that. Here's a glass if you need it. I'm going to measure out mine too.
It'd be helpful if I could read.
Uh-oh. I might hog.
Just need a little bit more.
Be careful. You might have a cornstarch fight. It could get ugly out there. Whew.
Okay, so that's about 45. And then I'm doing 30 mils, or I'm doing.
You're doing 30.
The 23.
You're doing 30. The first one.
Okay.
I'm doing 23.
Okay, I need another beaker if you've got one. Thank you.
Yep.
Thank you. Thank you. Oof. Bubbles.
Yes.
30.
Thank you.
And then I'm just mixing it together.
Mixing it together.
This doesn't seem like it would be easy.
Do. All right. I'm doing 23. The great thing about this, you guys, is it's all using ingredients that are relatively inexpensive for your classroom, readily available. Most kids have cornstarch at home. They could always use flour. It'll be a little different. Most kids have dish soap, and it doesn't have to be an expensive variety and be something inexpensive. But it can get tough when you're mixing it up here. And what we're asking our students to do is to observe the differences between these 2 cups based upon the amount of the liquid detergent that you put in. So after they've made the observations of you using borax and glue, they can begin to think a little bit about, okay, more or less glue. What should I see? What could happen with this particular polymer?
Ugh. Looks like icing,
Yeah,
but I'm not going to taste it.
I bet it doesn't taste like icing. Although, yeah, that would
Although
be
maybe
a
it's
great,
kind of like that paste we were just talking about.
that
I
would
don't
be
know.
a great April Fool's joke for someone that maybe. So that's funny. All right, so eventually you do want to pull it out of your hand, and you are going to make a little oobleck here, I suppose, except for you're using dish soap instead. And notice that mine is already a little drier than Jane's.
Mine's a mess.
I did that on purpose, you guys, just so you know.
Yep.
All right, so
Mine's
as you're
not getting any drier. I'll get Heather back. I will get her. Will not be. There
we
will
have
be a
7
payback
minutes.
here.
All right, so anyways, you guys, as you're kneading it, there still have the capacity to go ahead and see how you're still building up those chains with this kneading. So you're adding energy to your polymer, right, as you're doing this kneading exercise.
Oh, man.
Yeah.
This is gross.
I'm sorry. It's so, oh, it's a good day. Anyways, do you like, I don't want to switch you. Sorry.
No, I'm not switching. I'm just going to stand here now because I can't even do anything.
So when we're doing this activity, this is a great way for students to see how you can make different properties using the same ingredients. If they were to use less dish soap, could they make an even more solid-like substance? With the substance that I've made here, what you see is almost a non-Newtonian type of polymer, and that so non-Newtonian means that it exhibits more than one state of matter. So does it exhibit properties that are like solids and properties that are like liquids, for example? So as I continue to manipulate my cornstarch polymer here, it's beginning to dry out as I'm pushing more oxygen into it, kneading it up just a little bit. And you can almost, over time, get it to keep more of that round shape. And it'll continue to do so as you dry that out. Of course, now it just plopped on me.
Well, that's better than what's going on in my hand, so I'm just saying.
Jane has a little bit more work to do.
Yeah, I'm not doing any more work with this. I don't recommend the 30. That's what I'm going to say.
Well, so don't
lick it, not looking at it.
So in your classroom, maybe you start off with 23 milliliters, okay, and you could add less. So the thing that's difficult about that is just making sure that each students mix all of the dish soap up into the cornstarch, okay. So I'm going to put my product down here for cup number 2. And even though it's still exhibiting more liquid-like states of matter, so the properties of liquids, it will only go so far. Where it's like water, it would certainly spread out much further. Okay, so you start to see some properties of a solid material as well. Yeah, so we had a question about using dish soap over water. Dish soap does exhibit some different properties when we're thinking about states of matter. But the beautiful thing about cornstarch is because of the polymer that it is, little water is similar. So it certainly would be cheaper to use water, but you'll see something just a little slightly different. Yeah, so as students are washing up their hands with this particular activity,
this hand.
Remember, these are all water-based materials. Even with this, well,
so it should dissolve.
Yeah, it should come right off, and just with some soap and water, everything should be fine. But because we're running short on time here, you guys, we have 4 minutes left in this particular workshop. We just want to say thank you as we're moving along, and any information that you could put in the chat would be fantastic. Helping us as we edit out some of the tweaks. We'd love some of your expertise from your classrooms, because especially you're with the students, and right now possibly not with your students. So remember, these lessons were all designed to be made with students in the classroom in normal conditions, but we are hoping to differentiate them out so that they can be used in virtual settings as well, okay? And in addition to that, we just want to have some of your input as to how these lessons can be used in your classroom. Are they meeting needs for STEM type activities or problem-based learning or even hands-on inquiry-based activities? Are there certain standards that you would like to see addressed in a better way than what you'll see with some of these? as well, and just different differentiations at different grade levels, because this is a K through 6 based learning activity that we're seeing here. Some of them certainly range a little bit more as they're currently written for 6th grade or 5th grade, and some of them range down a little bit too. So just different ideas that you have on differentiation of those activities is also fantastic. Gosh, that
And
was
again,
quick.
yeah, we just really want to thank you for hanging in there with us. We know this is a busy time for you, and there's
Mhm.
a lot of demands on all of that time. So we are really appreciative. We're appreciative of UJEEP for being a
Mhm.
sponsor of this workshop, as well as the OSLN STEM Learning
Yep.
Network